Now we talk about integrated rate law. We'll start from a very simple example. Consider a reaction of A decomposes or decay to products. The reaction rate is equal to K times concentration of A with the power of nth. Anyway, this formula shows the rate depends on concentration, but not the reaction time. We cannot track the reaction by the time elapsed in a reaction. The time is actually hidden inside the expression of concentration change over a period of time. How can we get the reaction dependence on time? If we integrate the rate law equation, we may find the concentration dependence on reaction time. Then we can predict the concentration at any time. Consider zeroth order reactions. The power in the power law of rate is zero. Then the expression of rate law goes to minus dA over dt equals K. Because A to the zeroth is 1. Then we rearrange the equation and integrate it from A0, the initial concentration, to concentration at any time, At, from time at 0 to time t. We finally have concentrations of A at any time t equals the initial concentration minus K times t. Clearly enough, we now can calculate the concentration of A at any specific time, given that we have known the reaction constant K for this zeroth order reaction. For first order reaction of A goes to products, the differential concentration change over time equals K times A with the power of 1. Then we rearrange the equation and integrate as did before. We finally have At equals A0 times exponential minus Kt. Still, we can predict the concentration of A at any specific time. The last example for the reaction of substance A, the concentration change over time period equals K times A squared. After rearranging and integrating, we build the relation of concentration of A at any time to the reaction time. With these equations in hand, you can calculate the concentration of reactant at any specific time, or calculate the reaction constant through the data of concentration. However, the best way to get the reaction constant K is graphical approach, which could wipe errors out to the largest degree. You may find that the three integrated rate law have the form of linear equation. Y equals Kx plus B. Now, if you plot with the concentration of A versus time, the slope of the linear fitting line for the data is the negative K. If we plot log A versus time t, the slope of linear fitting line is the negative K. And if we plot inverted A versus t, the slope of the linear fitting line is the reaction constant K. By this graphical approach, we can determine the reaction constant quickly and easily.